5.4 differentiation rules for exponential functions. So we're just going to start by recalling some of the differentiation rules that we know. What were some of those called? Dun, dun, dun. Don't look back. Give you the first one. Product rule. The product rule says that if we have a function that is the product of two functions, then the derivative of that function is the first function times the derivative of the second function plus the derivative of the first function times the second function. So derivative of the first times the second plus the first times the derivative of the second. Then we have the chain rule. Chain rule is used when we have a function inside another function. So if we realize, let's write this a different way. If f of x can be written as g of h of x, so if we notice that f of x is actually a composite function, one function inside of another function, then the derivative of f of x is equal to the derivative of the outer with respect to the inner times the derivative of the inner. The derivative of the outer with respect to the inner times the derivative of the inner. We also have a difference rule. This one we kind of do automatically without even thinking about it. But if we realize that we are taking the derivative of a function that is a difference of two functions, so it's a polynomial or it's a string of addition and subtraction of different functions, then we can take, the derivative of that then is the derivative of the first function minus the derivative of the second function. It's just dealing with the parts of the function somewhat separately. And then this unit we learned that specifically for exponential functions, maybe just also d by dx, so the derivative of an exponential function is the natural log of b times the original function. So today when we're working with differentiation rules for exponential functions, we're going to be getting exponential functions, finding the derivative, and we're going to have to apply any one of these or multiple of these rules in order to do it. These are the key things to remember as we move forward. I'll leave them up there for at least the first couple. So example 1. Differentiate. There are 5 examples. They don't take a ton of space. First one is y equals x times e to the power of x. Okay, right away I see two variables. I see x in two different places, which shows me that this is the product of two functions. I have a function x times the function e to the power of x. So I'm going to apply the product of two functions rule, and I'm going to take, we're going to write the derivative. Oh, this isn't very good for a new marker. Soft. Anyway, we're going to take the derivative of this function by taking the first times the derivative of the second plus the derivative of the first times the second. Okay, so we have just the first function again, x, times the derivative of the second function. Well, we know that the derivative of e to the power of x is just going to be e to the power of x. E to the power of x is its own derivative. Then we're going to add the derivative of the first, which is 1, times the second function, which is e to the power of x. When we get to this step, so let's just note that we used the product rule. And now we're going to factor. So we notice that there's a factor of e to the power of x in both of these terms. So I'm going to factor that out, and that's going to leave us with x plus 1 inside the brackets. And that is fully simplified. That one is done. I'm going to work across just so I can fit a couple more on the screen here before moving down. B is y equals e to the power of 2x plus 1. So now I see a composite function. I have e to the power of x, but where I would have x in the exponent, I have another function, 2x plus 1. So I'm going to be looking at the chain rule because I have an inner function and an outer function. So when we're taking the derivative, dy by dx, I need to take the derivative of the outer function with respect to the inner function. Well, that's pretty straightforward. That's just going to be the same thing. E to the power of anything is its own derivative. So the derivative of the outer with respect to the inner is again just e to the power of 2x plus 1. And now I take the derivative of the inner function, which is our exponent 2x plus 1. The derivative of that is 2. Simplify, I get 2 times e to the power of 2x plus 1. So again, this stuff looks pretty tricky right at the start, but we're just applying the same rules and we're doing it very carefully. And we have the added maybe a little bit of confusion, still getting used to dealing with taking the derivative of exponential functions, particularly ones involving e. It's actually easier with e than with another number because this, when you're dealing with a base of e, the natural log of e is just 1. So that's why it's just itself. When we get different bases, which we have coming up soon, then you'll have another kind of factor in there, another thing to multiply by. At any rate, we're doing good so far. Let's keep going. C. C says y equals e to the power of x minus e to the power of negative x. All right, I see two functions. So I have a difference rule happening. The first function is really easy. It is its own derivative. And then the second function is actually a composite function. It's e to the power of x, but x is negative x. So I have a function inside a function. So I'm going to apply the chain rule there. So to take the derivative, dy by dx. It's the derivative of the first function, which is just e to the power of x, minus the derivative of the second function. And the second function is going to be the derivative of the outer with respect to the inner, which is just e to the power of negative x, times the derivative of the inner. The derivative of negative x is negative 1. So if we simplify this, I just have negative 1 times this negative factor, which is positive. So I'm going to have e to the power of x plus e to the power of negative x. And that is simplified. That was the difference rule and the chain rule. Difference rule and chain rule. And over here on example B, we used the chain rule. We had a composite function. D. D is y equals 2 times e to the power of x times the cosine of x. All right, so we have an exponential function and a trigonometric function, a sinusoidal function, and we have the product of two functions. In the first function, I also notice right away we have a constant multiplier. They're pretty straightforward. So let's do this. It's the product rule. We're going to take the derivative of the first, dy by dx. Derivative of the first times the second, plus the first times the derivative of the second. So the derivative of the first one is itself. It's 2e to the power of x. Times the derivative of the second. Do we remember the derivative of cosine?
Negative sign.
Negative sine x plus the derivative of the first. It is its own derivative. Sorry, I think I misspoke. I think I already tried to take the derivative of the first, and then I was supposed to do the second one, not derived, but I did it backwards, so but that's okay because it's its own derivative. So we're just going to say this is the first times the derivative of the second. Now I need to take the derivative of the first times the second. And we'll simplify this. I notice that there is a factor of 2 times e to the power of x in both of these terms. So I'm going to factor that out. That's going to leave me with, and I'm going to rearrange my two terms just so that I have a positive first. Inside the bracket, I have cos x minus sine x. We'll just recount what we did there. We have a product law, and then we factored. Last one for example 1 is e. It looks pretty scary. X squared times 10 to the power of x. So now we have a power function, the product of a power function and an exponential function, and the exponential function's base is not e. So we'll have to remember what to do with that. We'll be using this rule up here. So it is the product rule. We're going to be using the derivative of the first times the second, and then the first times the derivative of the second. So the derivative of the first here is 2x, just times the second function, 10 to the power of x. Then we're going to add just the first function copied down times the derivative of the second function. So the derivative of the second function of an exponential function b to the power of x is the natural log of b, in this case 10, times 10 to the power of x. And we're going to keep exact values, so I'm not going to calculate out this natural log of 10. We're going to leave it as the natural log of 10, which just so that we're remembering it's the log of 10 with a base of e. And then we're going to notice that we have common factors here, so we're going to factor out 10 to the power of x, 10 to the power of x, which is going to leave us with 2x plus x ln 10. Oh, and actually I'm not done. I'm going to erase this. There's one other factor, so we have a factor of x and two factors of x. So I'm going to factor out one of those factors of x. Sorry. So our factoring out becomes x times 10 to the power of x, which leaves us with 2 plus x ln 10. What did we do there? We used the product law, product rule, and then we factored. So not super challenging, but definitely have to be careful, and I'm sure you'll get more challenging ones in your practice problems than this. That'll stretch you a little bit. In example 2, we're going to use our differentiation skills to find extreme values of a function that involves an exponential function. Of course, it'd be pretty boring to do a problem where you just had to find extreme values of an exponential function, because there aren't any. Yeah, keeps going forever. Although I guess it has a limit here, but not not going vertically. And then this guy is same situation. That'd be pretty boring. So we're going to actually work with a composite function. And we're going to identify the local extrema of f of x equals x squared times e to the power of x. Okay, so this is familiar. We've done things like this a whole bunch of times. In order to determine where the local max and min values occur, and we're going to be getting the values as well. So we're looking for points at the end of this example. But the first thing we need to do is differentiate the function and then set it equal to 0. That will tell us when the slope is 0, right? The derivative function gives us the slope of the curve, and where the slope of the curve is 0, that will be a max or a min. So step 1, finding f prime of x. It's a composite, sorry, not a composite function, it's the product of two functions. So I'm going to take the derivative of the first, which is 2x, times the second, which is e to the power of x, plus the derivative of the second, which is its own derivative, e to the power of x, times the first, which is x squared. I'm going to set that equal to 0. And in the next same step, I'm going to factor it. So I see e to the power of x and a factor of x in both terms. So I'm going to factor out x e to the power of x, which is going to leave us with 2 plus x. And now here we have to notice that we found 3 factors. Okay, we've got a factor of x, we have a factor of e to the x, and we have a factor of 2 plus x. So what we need to do is consider all of the cases to find all of the solutions. That means all the values of x that will cause this whole side to equal 0. So either x is 0, that one was easy, or e to the power of x is 0, or 2 plus x is 0. So we're going to consider all cases. Consider all cases that make the equation true. Case number 1, and these are just going to align with the factors that we found. So case 1 is when x equals 0. That one's pretty easy. There's a solution. X equals 0. Case 2 is where e to the power of x equals 0. What can you say about that?
Never happens.
Can't happen. The range of e to the power of x is y values greater than 0. So that's never going to happen. We can do a quick little sketch here just to think about it. Range of e to the power of x is y values greater than 0. Therefore, no solutions. If we're still not sure that what I'm saying is true, you can just draw yourself a quick little sketch. E to the power of x looks like that. Never equals 0, never touches 0, never crosses 0, so no solutions in that case. Head to case 3. Case 3 is where 2 plus x equals 0. Subtract 2 from both sides. X equals negative 2. Okay, so we found our 2 solutions. 2 solutions are x equals negative 2 and x equals 0. But what we still need to find out is if these actually are local extrema, if they actually are a min or a max, which means we need to find out if there is a change of sign in the slope on either side of the critical value. So in order to do that, we're going to let these guys divide our number line into 3 intervals. So we're going to consider 3 intervals. We've got x to the left of -2. X is less than -2. Then we're going to have from -2 to 0. So x is greater than -2 but less than 0. And what's happening to the right of 0 when x is greater than 0. And we've done things like this before. We're going to take a test value in each of the 3 intervals, find out the sign of the slope, and that will tell us if there is a change of direction at these points, which would then make them an actual local max or min. So test value for x less than -2. Let's test x equals -3. Again, we're going to be putting this in our derivative function. So we've got f prime of -3 is equal to, and I'm just going to sub in -3 wherever I see an x. So I've got 2 times, in brackets, -3 times e to the power of -3 plus e to the power of -3 times x, times -3 squared. I probably could have used the other, probably would have been better off to use this one where we've already factored it out. That would probably be easier. I'll do that for the next one, but I didn't do it for this one. No big deal. This is going to be -6 e to the power of -3 plus 9 times e to the power of -3. You could even just factor it out now, which, if you want to write that step, would give you e to the power of -3. And then in the brackets, you'd have -6 plus 9, which would be 3. So we're looking at 3 times e to the power of -3, which we can put in our calculator and get an approximate value of 0.1. This would end up being, if you could do another step in your head, really, this would be 1 over e cubed times 3. You'd have 3 over e cubed. Would be an easy way to put it in your calculator. Okay, so that tells us that the slope of the tangent over this interval is positive. Therefore, slope of tangent is positive. Okay, I'm going to repeat those for the other 2 intervals. I'm not going to show the work, but for the interval between -2 and 0, we're going to test x equals -1, which means that we're going to take our derivative function and plug -1 in there. If you do that carefully, again, start with the factored equation this time. If you do that carefully, you will end up with -0.4. So the slope of the tangent, therefore, slope of tangent over this interval is negative. Last interval for x greater than 0, test value x equals 1. Take your derivative function, sub 1 in, use careful calculation, you should get 8.2. Slope of tangent is positive. Okay, you could probably do this underneath, but because I don't have a lot of space, I'm just going to do it right here. I just want to make a quick summary chart for what we found out. So here's our intervals. Okay, we chose test values of -3, -1, and 1. We found that the sign of the derivative over these intervals was positive, then negative, then positive again. What does that tell us? Well, that tells us that the original function is increasing, then decreasing, then increasing. Because we have a change of sign of the slope at these points, we do have local extrema, and we've identified which type. So at x equals -2, we have a max, and at x equals 0, we have a min. Maybe that's a helpful way to think about it. The last thing that we need to do is find the value of f of x at these critical values in order to give us the actual points of the local minimum and local maximum. So I'm just going to clear this and carry on. So again, the last step is to find corresponding values for f of x for each of our x values. So let's plug in our minimum first. We'll sub x equals 0 into f of x. We get f of 0 equals 0 squared times e to the power of 0. I don't care what e to the power of 0 is, it's 1, but it doesn't matter because I have 0 squared, which is 0, so this is 0. Therefore, we have a minimum at 0, 0. For our next one, for our maximum, we're going to sub x equals -2 into f of x. That looks like this. F of -2, got -2 squared times e to the power of -2. That is 4 over e squared, which comes out as, we'll just leave it. That's an exact value. Good. Therefore, maximum at the point -2, 4 over e squared. And yeah, we could get a pretty good sketch of the function at this point as well, if we needed to. Example 3. We're dealing with depreciation. Depreciation of a motorcycle. We have Laura. I wonder why all the motorcycle drivers in this book are chicks. Almost every time. Laura just bought a new motorcycle. Initial price, $10,000. $10,000 purchase price. The value of the motorcycle depreciates over time. The value can be modeled by the function v of t is equal to 10,000, there's our initial price, times e to the power of -t over 4. So one little thing that might look a little bit tricky is e is a number between 2.71 and 2.72. So it looks like a growth rate, but the exponent is negative. So actually it's the reciprocal, and this value is in the denominator. So it is a decay rate. This is a depreciation. V is the value of the motorcycle after t years. A, rate of depreciation when Laura drives it off the lot. So the initial rate of depreciation. The rate of depreciation is the rate of the change of value of Laura's motorcycle. It's the derivative function of the value function will give us the rate of depreciation function, and then we'll have to find it when she drives it off the lot. So first thing we need to do is take the derivative of our value function. Taking the derivative of this looks pretty tricky at first. It is, so we have a composite function, so we're going to use the chain rule, and we have a constant multiplier rule. So the first thing I'm going to do is just take that 10,000 in front and not think about it anymore. And then here what we have is the derivative of the outer with respect to the inner, and that one's pretty straightforward because that's e to the power of anything, which is its own derivative. So the derivative of the outer with respect to the inner is just copying that down again. And then the derivative of the inner is the derivative of this exponent. And that looks challenging as well, but what we have to realize is that, and just thinking off to the side, that this is really negative 1/4 times t, right? Negative t over 4 is 1/4 of t. Well, the derivative of this is just negative 1/4. So we're going to multiply this whole thing by negative 1/4. Which now if we simplify, we end up with 10,000 divided by 4, and it's negative. So we have negative 2,500 times e to the power of negative t over 4. So now this is the function for the rate of depreciation, and we want the rate of depreciation when Laura drives it off the lot. So we actually want to sub in t equals 0 because this is the initial rate of depreciation. So we're going to go for v prime of 0. So everywhere we see t in our new rate of change function, we're going to sub in 0. E to the power of 0 is 1. 1 times negative 2,500 is negative 2,500 or negative 2,500. So when Laura drives this motorcycle off the dealer's lot, it is depreciating at a rate of $2,500 per year. Initial rate of depreciation is $2,500 per year. B says Laura has decided that she is going to stop paying for insurance. She's going to stop her insurance coverage for collision once the motorcycle has depreciated to 1/4 of its initial value. So she wants insurance on it while it's still pretty new, but once it's only worth 1/4 of its value, she doesn't want insurance on it anymore. So we're trying to find out when should she stop her collision coverage. So collision coverage stopping when I'm just going to cheat, say 1/4 of value remains. When is this? Well, first of all, we think about what is 1/4 of the original value. 1/4 of 10,000 is 2,500. So when it's worth $2,500, she's going to stop paying insurance. So we actually need to go back into our original equation, the value of the motorcycle, and we know V of t that we're looking for is $2,500. So we have 2,500 equals 10,000 times e to the power of negative t over 4. And from here, we're going to use our algebra skills and our skills with logarithms in order to determine the exact value of t. So first step is divide both sides by 10,000. I'll give us 0.25 on the left, and on the right we'll have e to the power of negative t over 4. Now we need to take the natural logarithm of each side. What that's going to allow us to do is eliminate this and just equate it to the exponent there. So we're going to take the natural log of both sides. We have the natural log of 0.25 on the left. On the right, we have the natural log of e to the power of negative t over 4. And the reason this works is because this is now the log of e with a base of e. So we're really asking on the right, what exponent do I need to give e in order to get e to the power of negative 2/4, which is obviously just the exponent negative t over 4. So now we have the natural log of the natural log of 0.25, which we can do in our calculator. It's a real world situation, so we're good with an approximate answer. We get negative 1.386. And then over here we have negative t over 4. And we probably want to make a little note of what we did here. Step 1 is divide both sides by 10,000. That's easy. And then over here is take the natural log, the ln, of both sides. You're going to want to remember that trick. From here, to find out what t is, I'm just going to multiply both sides by negative 4. That gets us a t value of approximately 5.5. So if Laura doesn't want to pay collision insurance on this thing after it's lost 3/4 of its value, then she's going to want to cancel her collision coverage after approximately 5.5 years. Laura should cancel collision insurance after about 5.5 years. And we have one more little section to do. We're going to look at C. What is the rate of depreciation at this time? Rate of depreciation at this time. So then all we need to do is take our rate of depreciation formula, which is right here, and sub in t equals 5.5. So v with respect, v prime at 5.5 is equal to negative 2,500 times e to the power of negative 5.5 over 4. You can probably carefully type it into your calculator just like that, or you can do it piece by piece. So you can leave that negative 2,500 out and then simplify your exponent for e, which would be negative 1.375. Then you could do that calculation. E to the power of negative 1.375 is 0.25. And then you can multiply those together, you'd get negative 632, which tells us that after 5.5 years, 5.5 years, rate of depreciation is about $632 per year. Okay, a couple of key concepts. Differentiation rules that we've been working with all throughout the course apply also to functions involving exponents, exponential functions. And in the same way, we can use first and second derivatives to analyze functions and to solve real-world problems. And there is one other note there that I think we did right, but just in case you want to write it again or double check that we wrote it, there's a little note that says if y equals e to the power of f of x, so this is a composite function where the exponent is another function, then what do we know? Then y prime is e to the power of f of x, that's the outer with respect to the inner, the derivative of the outer with respect to the inner, times the derivative of the inner, which would be the derivative of your second function here. Pretty straightforward. Practice problems can be found on page 282, and you are responsible to know how to do 1 through 14.